Good morning, everyone. Myself, I am G. Charan from Tripoli branch. Today's my tech talk topic on AC machines is designing decentralized load frequency controllers and optimization approach for synchronous generators in landed grids. Designing a decentral load frequency controller LFC load frequency controller for synchronous generators in landed grids is a complex task that requires careful consideration of system dynamics, control strategies, and optimization techniques. Here is an outline of an optimization based approach for designing a decentralized load frequency controller. First one, there are several steps to know, and first one, system modeling. Develop a mathematical model that represents the dynamic behavior of the landed grid with a synchronous generator. This model should include the generator dynamics, governor response, turbine dynamics, and load dynamics. Consider the interconnections between different generators and the load buses. This model should include the generator's dynamics, governor response, turbine dynamics, and load dynamics. Consider the interconnections between different generators and the load buses. Here one second one, objective function. Define an objective function that captures the control objectives of the load frequency controller. Typically, the objective is to minimize the frequency deviations and tie line power imbalances in response to load variations and disturbance. The objective function should balance the trade off between stability performance and economic consideration. Third one, decentralized control structure. Divide the landed grid into control areas, with each control area having its own decentralized LFC, load frequency controller. This allows for local control action without requiring extensive communications and coordination among control areas. Con- Fourth one, controller design. Develop decentralized load frequency controllers for each control area based on an optimization framework. One approach is to use model predictive control. The full form of MPC is model predictive control or linear quadratic regulator. LQR full form is linear quadrate regulator techniques. This control should utilize feedback signs such as frequency deviations and tie line power flows to compute approximate control action. Fifth one, optimization algorithm. Employ an optimization algorithm to solve the formulated optimization problem. The algorithm should take into account the constraints of the system, such as generator limits, control signal saturations, and ramp rate limits. Common optimization technique include gradient based methods, evolutionary algorithms, or practice swarm optimization. Sixth one, simulations and validations. Implement the decent implement the design decentralized load frequency controller in a dynamic of the landed grid. Perform extensive simulations to assess the performance of the load frequency controller under various load variations, disturbance, and system conditions. Validate the controller's ability to maintain frequency stability, minimize tie line power deviations, and handle disturbance effective. Seventh one, sensitive analysis and fine tuning. Conduct sensitive analysis to identify the impact of parameter, various and uncertainties on lower frequency controller performance. Fine tune the controller parameters based on the sensitive analysis results to enhance robustness and ensure optimal performance under different operating conditions. Experimental implementation. Once the controller designs is validated through simulations, consider implementing the decentralized lower frequencies converter in a real time hardware in the loop. HIL full form is hardware in the loop or laboratory setup. Evaluate its performance using real world data and make any necessary adjustment based on the practical consideration and system response. It is important to note down that designing a decentralized low frequency controller for synchronous generators is landed grids requires expertise in power system dynamics, control theory, and optimization technique. It is recommended to collaborate with domain experts and conduct through research to ensure the effectiveness and reliability of the control design. Designing a decentralized low frequency controller for synchronous generator in island grids requires a systematic approach to ensure optimal performance and stability. An optimization approach can be used to design a decentralized low frequency control that provides an optimal response to load change and disturbance in grid. The following steps can be taken to design a decentralized low frequency controller using an optimization approach. First one, modeling the system. First step is to develop a mathematical modeling of the system, include the synchronous generators and the load demand. The model should capture the dynamic behavior of the system and simulated annealing. The choice of algorithm depends on the complexity of the problem and the desired level of accuracy implementing the controller. Once the optimization problem has been solved, the decentralized low frequency controller can be implemented using a distributed control scheme. The controller should be designed to ensure that each generator responds to a change in load demand in a coordinative manner. Testing and evaluation. Finally, the performance of the decentralized load frequency controller should be tested and evaluated under different operating conditions. This involves simulating and the response of the speech to various load changes and disturbance and assessing the stability and the performance of the system. Designing a decentralized low frequency controller for synchronous generator is landed grid involves optimizing the control systems of maintain a stable frequency and balance the power in grid. Here's an outline of an optimization approach to scale. Overall designing Overall, designing a decentralized low frequency controller for synchronous generator is islanded grids requires a comprehensive understanding of the system dynamic and a systematic approach to ensure optimal performance and stability. An optimization approach can be used to design an effective controller that provides an optimal response to load changes and disturbance in the grid. System modeling. Develop a mathematical model that represents the dynamic of their synchronous generators in the island grid. This model should capture the relations between frequency, power output, and control input. It's important to note that designing a decentralized load frequency controller for landed grids is a complex task that requires a thorough understanding of power system dynamics and control theory. It is recommended to consult with experts in the field and conduct extensive testing and validation before deploying such a controller in the real world application. Thank you.